Do a two-parter today. Okay?
Oh,
Two-parter.
shoot.
Okay. Let's go. There you go, Tommy. All right, here we go. Let's start off with this differential equation. And just kind of have a throwback to things that you've done in the past. We'll do all of these real fast. What was that?
Slope fields.
Yeah, slope fields. All right, Bob. So, Bob, if I wanted you to make a slope field with this differential equation, right?
Yeah.
Oh, yeah.
If I was at x equals 1 and I plugged 1 in right here, what would all these slopes be?
0.
0, right? You'd come over here, you'd be like, all right, I got a slope of 0, got a slope of 0, got a slope of 0. How would you do all these slopes here, Bob?
It'd be a positive one.
Yep, you'd positive 1, so it should be like 45 degrees, 45 degrees, 45 degrees. And what happens if you plugged in 3?
Slope of 2.
Slope is 2, a little bit steeper, right? Up 2 over 1, got it. Cool. And then you could even do these over here. You'd be at what if you plugged in 0?
Negative 1.
Negative 1, 45 degrees. Perfect. Baba, bonus question. Why did we talk about slope fields last year?
Let's have Andrew have a shot this one. He seems to know.
What'd you say? Andrew, why?
Gives us a visual of what the integral looks like.
What the function looks like, right? Yeah, yeah. If you integrate that, you know.
Yeah, yeah.
Were all differential equations solvable?
No.
No, right? Not all of them were. There are ways to do things, but it's not in this realm. That's when you get to differential equations. Okay. All right. So, with all that being said, so Andrew, you got the slope field, right?
Yep.
Feel good about that?
Yeah.
Andrew, if they said something along the lines of, well, let's just do this because this is how it pops up on the BC exam, just so you know. Slope fields. Remember this kind of question right here? Find the particular solution.
Yeah, you just plug it in.
Right? Find the particular solution and they give you a point, say like f of 0 equals 2. What did that mean? This is how they sneak it in on the BC exam. Euler's method. We haven't gotten there yet, but it's coming. Do we need to do separation of variables? Find the particular solution. Find what the original function looks like.
Or if it's multiple choice, can't you just like plug it in?
No, this is FRQ. Yes, if it is multiple choice, you could. But, so, Hans, you remember how to do separation of variables?
Oh, yeah.
Would I just multiply by dx?
Yeah.
Right? You multiply by dx over here to the other side, and you're like, okay, I can integrate this. You integrate both sides, you're gonna get, I gave you a nice and easy one, y equals x squared over 2 minus x plus c. Hans, what would you do from right there?
Plug in 0, and C should be 2.
Yep, you plug in 0 and c would be 2. Did you chat GPT that right there, Hans?
Oh!
Oh, get roasted.
Perception is everybody's reality, Hans.
Yeah.
Remember
I
that.
should get meta glasses. You should not get meta
I can only imagine.
All right, so
Everybody perceives me
with
as
that
a
being
cheater.
said,
I should
Hans.
double down on cheating.
Okay. With that being said, we got to talk about a few other things. Just so, I mean, like, let's dive deep here just for a second. Got to go to the deep end. Hans, you know what this formula is?
Oh, that's the vertex. No.
It has something to do with it. It'll help you find the
It's-
vertex.
I can't remember the name of this one, but it's
Come on, we got if you're in Calc 2,
it's how
you
you
got
get the
to.
x coordinate for the vertex.
I know. What's the name of this formula? Axis of symmetry. Okay, it is the axis of symmetry. And being in Calc 2, you guys should know where this comes from. What about the quadratic formula? What called?
The derivative.
The derivative.
Ah.
Remember doing that, Baba? Right, Baba? If I had the standard form for a quadratic, right, and I took the derivative of this, you'd have 2a x plus b, and if I set the derivative equal to 0, that's how you get negative b over 2a. And doesn't the axis of symmetry always go through the vertex?
Yeah.
And Baba, if you're talking about a vertex of a parabola that opens down or opens up, what do you know about the slope of the tangent line of the curve always at the vertex? 0, right? That's where that formula came from. Okay, now Baba, the reason why I just bring that up, one, I feel like you should know that. Two, if I just wanted to graph this thing real fast, like, and I was like, all right, negative b. B is the in front of the x, so it's already negative, so it's 1 over 2 times a. I get 1 for the x coordinate. Hans, this is the x coordinate of the vertex. How do I find the y coordinate of the vertex?
You plug it back into the original.
You plug it back into the original, right? As soon as you plug it back into the original, you're going to get 1/2 minus 1, which is negative a half plus 2, 3/2, right?
Yeah.
So here's your vertex. Now, if you just came back over here to this fancy slope field, right? They told us it crossed through at 0, 2, right? And we just found the vertex at 1, 1.5. And I don't know about you, but this looks like a pretty good slope field, right? For the original graph, for the original function. Remember back in last year, they would always like give you a point on the graph somewhere. They'd say draw, you know, the particular solution that crosses through that point.
Yeah.
You'd have to follow the slope field. Yeah. Well, here we were able to actually solve for it and all that other fun stuff. How do we feel about that so far?
Good.
Okay. Now, what happens when some differential equations are pretty hard to solve? Well, Euler's method comes into play. It's pretty nice. Good? Okay. Here's what we get to do now. All right. Here's how the directions change with Euler's method. They will say use Euler's method, starting at x equals 0 with 2 steps of equal size to approximate f of 0.6. And you're like, what in the world are you talking about, Mr. Baker? Well, if we're starting at x equals 0, Hans, what do you know about x equals 0? It's 2,
It's 2.
right? But if we're starting at 0 and we're going up to 0.6 of 2 steps of equal size, what would be our how big are our steps if I'm going from 0 to 0.6?
0.7.
So you need to chat GPT that?
Negative 0.7.
Hans, hold on.
Be quiet. That's 1.4 and 2. What?
Hans, hold on.
What are you talking about?
6, 7.
Hans, if I'm going from 0 to 0.6, 2 steps of
Oh,
equal size.
0. Oh, 0.3.
0.3, right?
I did it 2 to 0.6. That's
I know,
where
I got you. All right, Hans, it's fine. All right, so Hans, I'm just going to show you the process, but I'm going to show you the visual of what's going on over here. Does that make sense? All right, so here's how Euler's method works. You always go to your first step size, which in this case is 0.3, right? How do I find f of 0.3? You always start with the beginning. We know what f of 0 is, right?
Yeah.
Right? We know what f of 0 is. And we're going to add our step size, right? We're going to add our step size. So this is like your starting point. This is your step size, right? And right here is the slope of your starting point, right? It's the slope of your starting point. So in this case right here, f of 3 would be 2 plus, right? F of 0 we knew was 2 from right over there. And what is the slope, Hans, at 0, right? If you're using this point to find slope, which one are you plugging in? The x coordinate or the y coordinate?
The x.
So what is the slope at 0?
Negative 1.
What was the slope at 0?
Negative 1.
It was negative 1, right? You see what I'm getting at? So the slope over here was negative 1. Do a little math right here. 2 minus 0.3 is 1.7. Now visually, here's what's happening, Hans, right? We started at f of 0, didn't we? Like we literally started at f of 0. And then we did a little step size of how big?
0.3.
0.3. We went right 0.3 and we did the slope of what? How much did we carry that? We carried the slope 0.3, but what was the slope?
Bless you.
Huh?
0.6.
Well, in this case it was like negative 1, right?
Oh, yeah.
It's almost like doing the slope of negative 1, just 0.3 of the way, right? And it actually ended us up where? Like at 1.7?
Yeah.
You know what I mean? In other words, like this, you had this line right here. Is that almost on the curve?
Yeah.
It's pretty close. All right, it's pretty close. Let's do another one. You'll see what's going on right here. F of 0.3 was 1.7. We graph that. Now, Hans, what happens if I wanted to do f of 6? Give me the setup here. F of 0.6. Where do we start?
Where we started f of 0.3.
Correct. You start with like your last point you just figured out. Plus what?
The 0.6 times f prime of 0.3.
Well, do your step size. Starting
Oh, yes.
point, step size. What slope am I going to use? F prime of what?
0.3.
0.3, right? So which one of these are you going to use to find the slope of f of 0.3 when you plug it back into the formula? You going to plug in 0.3 or 1.7?
0.3.
What is 0.3 minus 1?
Negative 0.7.
Yeah, so we're going to have 0.3, negative 0.7. You have to get comfortable with decimals and or fractions, however you want to do it, because these questions are on the non-calculator portion, whether it's multiple choice or FRQs. They love these things, so I see it happen every year, Baba. People mess up on their arithmetic. So slow down. Okay, so Bob, what is 0.3 times 0.7?
Negative 0.21.
It is negative 0.21. And what do you when you subtract those, Bob?
Negative. Oh, never mind. 1.7 minus 0.2. Oh, 1.49.
1.49. Perfect. And Bob, it's really the same thing that's happening again right here. If I just went over my step size, right? We start here. That's where we ended last, isn't it?
Yeah.
At 0.3, 1.7. If I start here and I go 0.3 one more time, I end up at 1.49, which is just below a half, right?
Yeah.
Okay? See how we're doing like just repeated tangent lines?
Yeah.
Is it pretty close to the original?
Yeah.
Absolutely. How would you make your line even closer to the original?
Step size is smaller.
Make your step sizes smaller, right? Make your step sizes a whole lot smaller. Now, what you also got to understand too, Bob, is this is kind of like the birth of Taylor series, to be honest with you. We haven't gotten there yet. But could you write f of 0.6 as this right here? Right, Bob?
Yeah.
I mean, you see how we're doing, we started at our point that they gave us, and we're just doing repeated tangent line approximations. Like we could keep on going, you know, and make them smaller step sizes if we wanted to.
Yeah.
But does that make sense? Like this right here was basically just this whole part, wasn't it?
Yeah.
Or like the 1.7 part? And then we just add this. Like, so you could write the two step sizes honestly as one equation, right? You could write it as one equation and do it that way, but it is a repeated tangent line approximation. And just for fun, Bob, because you're really good at fractions, you want to know what the real value was? What happens when you plug in 0.6 to this equation over here? What's 0.6 squared?
0.36.
0.36 divided by 2 is 0.18.
Yeah.
Minus 0.6 plus 2. This right here would be a negative point what? 42?
Yeah.
What's negative 0.42 plus 2?
1.58.
1.58. So not too bad, right? We approximated it and got 1.49, but the actual value would be 1.58. Daniel, what do you think?
I like it.
You like it? It's not too shabby. But that's Euler's method. It follows the exact same thing over and over again. Baba, do you feel like you want to do another example of that, or do you feel pretty good?
I'm good about that.
Yeah, I mean, the only thing that you got to pay attention to, sometimes they'll have you start at 0, and they'll have you go to like negative 0.6. Your step sizes are now what?
Negative.
Negative, right? You just go, look, because you're going left, your step sizes would be negative. Does that make sense?
Yeah.
Okay, so you can go to the left, but it's all good. I mean, it's repeated tangent line approximation. All right? Good? Joseph, you feel good about that?
Right.
Whose number is that?
Back person.
Back person. Troy Aikman was number 8, wasn't he? Yeah. All right. Cool. All right, well, if you're okay with that, let's get to the fun stuff. We've got a two-parter today. Here's the second part.
Wait, why did we do this on partial fraction decomposition.
Alright, partial fraction and decomposition. Yes. Actually, that's funny, Cole, you said that. When I met with Miss Bartlemy this morning, she was, she asked how BC was going, and I told her what we were about to cover, and she's like, yeah, it's gonna be on our next test.
On our test?
What? I didn't say anything. So here we go. Let's just keep going.
Die.
Alright, real fast though. Porter, we gotta have a throwback. You ready? Porter, because if I feel like if I gave a pop quiz on this right now, there's still some dust out there that we gotta settle. Okay? What are we gonna do about this integral right here? What comes to mind, Porter?
Yeah, maybe break it up.
No.
How would you break that up?
Maybe not.
Just spread them out.
I don't know, I thought you said, but.
Inverse tangent.
Hans?
It's inverse tangent, I believe.
How in the world do you know that?
Well, because it's 1 over
look at Nate's.
u squared. I didn't look at
ChatGPT.
Nate's. I use, it's, no,
ChatGPT.
it's, what is it? It's u prime over, u squared plus a squared or something like that.
He looked at Alex's notes.
And what were you gonna say?
Factor it.
Can you factor that?
I don't know.
Are there factors of 4 that add to 2?
Wait, that's a 4. I thought it was a 1. It's
Nothing like that.
Yes, it does.
Alright, so Daniel, here's what I'm getting at, right? Like if we had to do this integral right now, you're kind of touching on some things here that you got to start paying attention to. Like Porter, if you could factor this,
Yeah.
you should probably factor it. Right? That's basically what we're talking about today. Partial fraction decomposition. But if you got a problem like this, and you're like, ooh, I can't factor it. Do you do long division?
No.
When do you do long division?
When there's something on top and then we can.
When what about the top though?
It's
The power are bigger.
When the powers are equal or greater on
Because
top.
you divided the top by one.
Okay, so you should do long division. I'm just kind of going back because remember those test averages that I threw up there. You know what I'm saying? Like there's just all the math comes together. You know what I'm saying?
Yeah.
Henry, you know what I'm saying? Yep. Okay, it all comes together. So I'm just trying to refresh your memory. So power on top is not even greater, so we're not doing long division. We can't factor. What was the technique that we used for this? Completing the square. Right? Completing the square. So with that being said, okay, remember that you would isolate the x's. You know what I'm saying? We'll show all the steps here. You isolate the x's. Leading coefficients 1. What do you do to the middle term?
Double it.
Divide it.
Half it in.
Half it in square.
Square it. If you half that and square it, you get 1.
And you
But
gotta
because I
subtract
added 1
one.
on the bottom, I should probably
Subtract it.
subtract 1 from the bottom, right? So this integral will just turn into 1 over, this factors nice and neatly now, x plus 1 squared plus 3 dx. Now, Hans,
Yeah,
that's what your mind was seeing right there.
yeah.
Okay, that's what your mind was seeing. Because if you remember back in the day, when we first did this in class, I'll get out of your way here for a second. When we did arctangent back in the day, we said it was u prime over, right, 1 plus u squared. Okay, that's how you take the derivative of arctangent, right, Porter?
Yeah.
Okay, but in this case, we also learned back in the day the integral expression, and it looked like this, right? So we don't need the du right there. But what was the formula? Does anybody know the formula? Because in case I gave you a formula quiz one day.
Oh, is it 1 over a?
Yeah,
Arc tan.
yeah.
Of. Is that absolute value of?
U.
It was a
It's u
Over A.
You over A?
I thought it was absolute value of u. Right?
See you.
You ordered together.
I think I was gone for that one.
What'd you say?
I think I was gone for that one last year. I think I
Okay.
was.
Well, good memory. Right, Porter? That's good, right? So Porter, with all that being said, come on, you can calc too. If I gave you a problem like this, you should be like, ooh, you should be eating that up. You know what I'm saying? In this case right here, Porter, you can't get lazy, right? Is u x plus 1?
Yeah.
Still go through your u substitution so you don't screw anything up. U is x plus 1, du would just be dx. What's a?
Oh, no, square root of it.
Square root of 3. So final answer here, what does this integral actually turn into?
1 over square root of 3 arctan of x plus 1 over
Over root 3? Porter, when we get to talk about trig sub, we can talk about why this formula makes sense. Like go down to the deep, deep end. Fish bricks out of this pool. You guys, yeah, the deep end. That you guys. I still remember saying that, but I might have.
So like at least 5 times.
Yeah, okay.
Just multiple times.
Multiple times. Fish and bricks out the deep end. But all right, Porter, how do you feel about that? Okay. So Porter, example number 1. Here we go. You ready?
Yep.
Let's talk about a different scenario. Okay, you look at this one and you're like, Mr. Baker, that looks exactly like the last one. And I'm like, yeah, it's pretty close. You know what I'm saying? It's pretty close. Number 1, can you factor that?
Yes.
That's probably the route you should go, right? That's probably the route you should go. Because Porter, don't write this down. Not that you have to, Porter. But let's say you just love completing the square. You're like, Mr. Baker, I can half the middle term and square it. Half of 5 and squared is 25 fourths. And because I added 25 fourths, I gotta subtract 25 fourths. And by the time I simplify this, you understand that you know, math is the study of patterns. You get x minus 5 halves squared right here. 6 minus 25 fourths is negative 1 fourth. And you're like, oh my goodness, I'm so good at what I do here. That's so close. Why isn't that arctan?
Because it's minus.
Oh, wait, that's square.
It's so stinking close. Why isn't that arctan?
Minus the square root of negative.
Because of the what?
Minus.
Because of that minus sign right there.
That.
Okay, it is not arctan because of that minus sign right there. Needs to be plus. Big deal. You got that, Baba?
Got it.
Okay, so that is not arctan. So let's go back to what we talked about. If you can factor it, that's probably the way you should go. Right? So this is how you do partial fraction decomposition. You ready, Henry?
Yep.
Henry, what factors of 6? Add to 5.
3, 2.
All right, so it goes into x minus 3, x minus 2, right? The whole idea with partial fraction decomposition is to break it up, right? I have one denominator right here, one factor, and I want to know what constant over x minus 3, when I add it to some constant b over x minus 2, it will equal this expression. Partial fraction decomposition really just means you're going to break apart a fraction right here that has a common denominator of x minus 3, x minus 2, and you're going to solve for these constants. Baba, today, notice that a and b are constants, and they're always 1 power less than the denominator, right?
Okay.
Like tomorrow, have a good breakfast and a good lunch, okay? Because tomorrow it's not always going to be like linear factors. See how these are linear factors?
I do.
Sometimes you might pull a GCF out, you might have a quadratic factor, right? Sometimes you might have like x minus 1 squared, you have repeated linear factors. So many things change. Today we're just getting our feet wet, okay? You got that, Baba?
Got it.
Now, Baba, this is like Algebra 2 back in the day, to be honest with you.
It is.
I know who your Algebra 2 teacher was,
Yeah.
right? If we were going to solve for a and b, you would basically cross multiply right here to get common denominators. You're like, this side has an x minus 2. What does this side want? An x minus 2. And this side has an x minus 3. You know what I mean? So like, as soon as you cross multiply, right? And we learned this back in algebra, Baba. As soon as you got a common denominator, did we care about the denominators anymore when we were solving? No, they just go away. We don't pay attention to them. We're just solving the numerators now, right? So we do cross multiplication. Now you might be like, Mr. Baker, you're silly. There's 3 unknowns up there in one equation. You can't solve that. Well, here's where you just get to have fun. What happens if I said x is 2? What's b?
Cancel these and solve b, which is just going to be.
What's b going to be?
Negative 1.
b is negative 1. Porter, what happens if I said x is what? 3. If I said x is 3, that goes. You now have 1a equals 1, so it looks like a is what? 1. Okay? The whole idea of you doing this is because you're really going to break this integral up into a over x minus 3, in this case, 1 over x minus 3, plus the integral b, in this case, which is -1. I'll just leave the -1 up top there for just 1 second. You can break this integral up into 2. Partial fraction decomposition. After there, it gets pretty easy. Don't get lazy though with U sub. Andrew, what was your question?
Alright, I didn't have a question.
What's the integral of 1 over x minus 3?
I wanted to know that's what I
Right? You'd have the natural log of x minus 3. And then what's, this -1 really lives out in front, doesn't it?
think.
So what's the integral of 1 over x minus 2?
Oh, sorry. Natural log of x minus 2.
X minus 2. Right? Now, because Mr. Baker can tell the future and things that are coming, and you want to get the right answer, Gabe, right? Especially when we start doing improper integrals and you see like infinities as bounds and all this other kind of mumbo jumbo. Okay, we're not there yet. Don't write your answer like that, because if you do, you're going to get the wrong answer when we start doing improper integrals and things like that. Subtraction is like what?
Division.
So you should write this as x minus 3 over x minus 2. If you can write it like that, you can remember your properties of logarithms, you won't get the wrong answer, which is good. Bob, how do you feel about that?
Getting there.
Okay, let's do another one real quick, Bob. All right, Baba, are we going to do long division?
No, because the power on top is not the same or greater than.
Great, that's good. So we're not doing long division. Can we factor the denominator?
Yeah.
Yeah, what do you factor that into? What factors is 6? Subtract 1.
-3 and 2.
-3 and a +2. Right? And the whole idea with partial fraction decomposition was you're just going to take your first denominator, right? Now, Baba, do some people put these backwards when they do it? 'Cause, like, what happens if you put x plus 2 right here? Are you still going to get the right answer?
Yes.
Yeah.
Yeah, it doesn't really matter. Doesn't matter, right? Plus b over x plus 2, right? Again, Bob, we talked about this. As soon as you cross multiply, basically, and get a common denominator, do I care about the denominators anymore?
No, they can go away.
No. So when I cross multiply right here, it looks like this. Okay?
Okay.
Baba, how am I going to solve for any of these? Just pick a number. Let x equal what?
Make it 3.
Okay, so if x is 3, you now have 5a equals 20. So what does a equal?
4.
4. Good. Let's let x equal -2. If you plugged in -2 over here, that goes away. But you're going to have -5b equals 5. So what's b? b is -1. Right? You cool with that, Baba?
Yeah.
So why did we do that? Well, this integral now looks like this. You would have a, which in this case is 4 over x minus 3. You would then have your b, which is going to be like a -1 over x plus 2. And Bob, what do we get? What's our final answer right here? 4.
4 natural log of x minus 3
Excellent.
plus.
Or just minus.
Or minus, yeah.
Natural log of
X plus 2.
x plus 2.
We know our properties of log.
Now, can you do subtraction like division?
What's the second one?
You could. Could you make this x minus 3 to the 4th and then divide?
We could.
That's not really a thing at this level.
Alright.
You don't need to do that. Like x minus 3 to the 4th power. Just leave it like that. You're okay right now. You're good.
Okay.
Okay? But Baba, let's say there was a 4 right here. Could you pull a 4 out as a GCF
And then, yeah.
and then do that?
Yeah.
You know what I mean? That's the idea. Okay? That's the idea. So we'll live right there for right now as our answer. Okay? All right, so real fast here. This is the last one. Just want to see if how we have a little race. Okay? Not that speed is everything in calculus. Okay, Porter. So Porter, if you've been paying attention today, you listened to Mr. Baker and his words of wisdom. Let's see what you got.
I don't remember what 2 squared though. Figure it out.
Okay, try it out. Andrew, you got one?
Yeah.
Let me come back there. You got it? Yeah. Folks, if you have a 4 out in front of your natural log, you are getting lazy with U substitution. Don't get lazy with U substitution. Yeah. There you go. Much better. Much better. Good.
That's good.
That's the right answer. So let's see. You got a definite interval.
Oh, it's definite. That was my integral, at least, right? I'm not super confident.
Why did Miss Brigger let go of the bike too soon? Huh? Zach? You gonna talk about it?
I'm figuring it out.
Jay, how did you get it?
I think so.
Brooks, you ready to talk about it? Brooks, let's just run through real fast. Brooks, did you factor the denominator? What'd you get, Brooks, when you factored that? You completed the square. Brooks, you don't complete the square. 4x is 4x and x, right?
It just doesn't freaking bots.
Okay? Right? Brooks, you follow me right there? Yeah. Okay? You can't factor that. If you do FOIL right now, you're gonna have 4x squared plus 5x plus 1, right? Just like we've been doing, you break that up, a over 4x plus 1, b over x plus 1, and then you set that equal to 3, right? Brooks, what do we do after this step? What do we need to do? You cross multiply to get like a common denominator, essentially, right? So you're gonna have a x plus 1, b 4x plus 1, and that equals 3, right? If I let x be -1, Brooks, what do you get here? That goes away. What's that turn into?
Yeah.
You'd have -1 times 4, which is -4. -4 plus 1 is -3. You divide by -3 to solve for b, and b is -1. What about -1/4, Brooks? What's -1/4 plus 1? 3/4. By the time you multiply by the reciprocal, a is what? 4, right? Okay. So again, don't get lazy right here with your u sub. A is 4, right? B is -1. Bobby, you follow me? Bobby, here's what I was talking about with u substitution, right? If you let u be 4x plus 1, don't get lazy, right? Because you got the 4dx up there. So this is the natural log of 4x plus 1 minus the natural log of x plus 1.
Oh, that's where I
Baba, what have I said about this today?
Longer than
Before you even try to do top minus bottom, FTC, should you write that as division? Yeah, go ahead and write that as the natural log of 4x plus 1 over x plus 1, and then evaluate that from 0 to 2, right? You're going to get 9 over 3, which is just the natural log of 3. When you plug in 0, you're going to get the natural log of 1. So final answer, natural log of 3. That's what you're going for. Okay?
This is too big.
What's up?
I figured it out. I got it. Yeah.
Bob, a lot of times this will be like 3 to 4 points on an FRQ, depending how hard it is. You know what I mean? Of like you just like showing your work, separating it, a point, solve for A and B, second point, you know, integrating correctly, third point, and if it's a definite, you know, they might have a point for the answer.
Sprague, I got a question.
Yes.
So on an FRQ, will it say like very specifically like use partial fraction decomposition, or how will it be worded on an FRQ? Like what will we?
They'll just
be-
have something like that.
They'll just have something like that.
They'll say evaluate the integral.
All right, that's
You know
good
what I
to
mean?
know.
That's why I'm just trying to get you guys to go through the thought process of like, how am I going to do that? You know what I mean? A lot of the times, they can kill 2 birds with 1 stone, to be honest with you. They can do this partial fraction decomposition with improper integrals
Oh.
when we start talking about that. And they do that a lot, actually. So it ups the ante. Yes?
Is there a telltale sign between, like when we use arctangent versus when we do?
If you can factor in the denominator, it's partial fraction decomposition.
And if you can't,
Complete the square. Or like long division, you know, if we had other things.
okay, and then
Yeah,
it's
yeah.
arctangent.
Yeah. Yes.
Would completing the square work too?
No.
What is that? Oh, that's
Because when you subtract it off, it's going to be a minus sign out there. Okay? Bob, you cool with that?
Yeah.
All right, we just did 2 days in 1. How do you feel about that?